Okay, we're recording. It's still on the screen. Hopefully we're good to go here. Okay, all right. So, picking up from where we left off last time, a quick reminder, of course, don't forget about the attendance code, attendance quiz. Hopefully you all have routines for that at this point. So let's talk about this idea of direction of fastest increase, direction of steepest ascent. It comes from considering a pretty natural question. The question we're going to consider is, suppose we have, some function f, and suppose that in the domain of that function we are at a particular point. And perfectly reasonable question to ask, okay, there I am. Which direction should I go to make this function increase the fastest? Now let's just take a moment to dwell on what an extremely natural question that is. Right? So this might represent my location, or it might, by its coordinates, represent the current state of a system that I'm looking to maybe tweak, or something like that. Right? But this is represents the current state of being in some sense, and F represents something that I want to make as big as possible. So it's very reasonable to ask in which direction. Looking at unit vectors to, we don't want to factor in speed. Obviously, if you move faster in the input, you'll move faster in the output. That's not what we're interested in. We're just interested in directions. Of all those unit vectors, if I want to maximize the directional derivative, namely how fast the function changes, right? How do I maximize that directional derivative? So which one? Perhaps this one maybe. Which one of those unit vectors will maximize that directional derivative? Does everybody understand the question before we dive into the answer? Okay, so a reasonable thing to ask. Now, before we get into the answer, let's talk about a little terminology. How do I describe this answer that we're looking for? And there's a couple different ways to do it. First of all, let me note that directional derivative that we're trying to maximize, on the one hand, it represents how fast the function is changing, right? So if you're trying to maximize how fast a function is increasing, doesn't it seem reasonable to call this direction the direction of fastest increase? Because it's literally the direction in which the function is increasing the fastest. Right? I think it's a very natural phrasing. To my surprise, this is the less common of two terms used to describe this. The other comes from thinking of the directional derivative in a different way. If you think of the directional derivative as the slope of the graph, and quick pause, reminder, y'all know I'm real uptight about, well, wait a second, what kind of a picture are we looking at? Is it a graph? Is it a level set? What are we doing? Right? So if you're thinking about F in terms of the graph, another little quick side note, we're not looking at the graph in this picture, right? So anyway, but if you're looking at it in terms of a graph, then directional derivative means slope of the tangent line of the graph. Sure. And if you think of that as being the slope, and if you're trying to maximize slope, doesn't it seem reasonable to refer to the direction that maximizes slope? That means you're going in the direction that's as steep as possible. And so with that in mind, they call this the direction of steepest ascent. This is the more common term. Now, my gripe with this is based on what I've already kind of trash talked this a little bit. We're not always looking at a graph, right? You don't want your intuition to be hung up on something that may be highly inconsistent with what you're actually doing. Right? So I don't particularly personally care for this latter term. I don't use this term deliberately anyway. I will confess, when I was y'all's age and I was learning this for the first time, that was a term that my teacher used, and so I've kind of got some of that drilled into me. But I think this is the better term, direction of fastest increase. And I want to encourage you to think in terms of that as well. Okay, all right, but anyway, be aware of the other one. Okay, so how do we do it? This is actually a pretty straightforward calculation. Here's the thing that we want to make as big as possible. Here's our formula for it. It's a dot product. Here's how we compute dot products. Don't forget, we were only looking at unit vectors v. All these v vectors have to be unit vectors, so that magnitude is just 1, which means that factor can just go away. And furthermore, don't forget that as we contemplate all these possible different directions that I might go from the point A, we are actually not yet moving from the point A. A is fixed for the moment. We're just kind of looking around, thinking about which way we want to go. Well, if A is constant, keep in mind that the gradient is evaluated at A. That means that this gradient here is constant because we are not moving yet. So, it boils down real simple. You want to maximize this directional derivative? Yeah, you just need to maximize cosine. Right? Specifically, the cosine of the relevant angle, and the relevant angle here is the angle between that vector and your gradient vector. So the relevant angle theta then is that angle right there. And how do you maximize cosine? You maximize cosine by letting the angle be 0. And if that angle is 0, incompatible with my picture, right? I didn't want to draw it as 0 because I didn't want to assume my conclusion. But if you think about what does that picture become if that angle is 0, well, what it becomes is that the ideal direction is that unit vector pointing in the direction of the gradient. Namely, it's that right there. So, very natural question. Pretty reasonably straightforward answer. The direction of the gradient is the direction of fastest increase. Okay. All right. Now, next natural question. Cool. So, yeah, okay, great. I'm going to go in the direction of the gradient. Nice. I want to make f increase as fast as possible. I'm interested in, therefore, how fast is it increasing as I go in this optimal direction? Right? Again, very reasonable question. We know which way we're going to go. In that case, this thing that I want to be as big as possible, what is it? And there's a really easy calculation you can go through here. Just take a look at this at your leisure. It's very straightforward. Again, directional derivatives are computed with a dot product, which, well, we know how to do algebra. And nice punchline is that maximum rate of increase is the magnitude of the gradient. So let's take a quick moment to recognize we asked two very reasonable, natural questions. What's the direction of fastest increase? And how fast is it increasing in that direction? And the answers were the direction of the gradient and the magnitude of the gradient. In some sense, in both cases, the answer was the gradient. And I think this is a noteworthy moment. So let's talk about that for just a moment. When we first wrote down the gradient, it was a bookkeeping shorthand. It was notation so that we didn't have to write down a bunch of similar looking terms, ... this kind of thing. It was just a convenience. It was notation. Now we have a much more natural, a much more geometrically relatable description of the gradient. The gradient has a direction and a magnitude, defined by its direction and its magnitude. As we just saw, the direction is the direction of steepest descent, fastest increase. And the magnitude happens to be how fast is the function increasing in that direction. Pretty unexpected, right? Again, when you write down a notational shorthand, you can't expect that it'll turn out to be something cool like this. So we got lucky. All right, let's see a quick example. This example is actually very straightforward, but there is a terminological thing I feel. Oh, did you have a?
Wait. So,
yeah.
Right now we're finding the direction of steepest descent. Is there any way of finding shallowest say.
Oh, you mean the fastest decrease?
No, I mean, that would just be the same direction the other way.
Yeah, exactly. Well, yeah, that's right. And then what you're describing is, in fact, the direction where it's not changing at all, and that would be sort of halfway in between them. So right angle. So that's the direction of fastest increase. That's the direction of fastest decrease. And any direction perpendicular to both. Again, just think, we're just doing dot products. So perpendicular means that the rate of change will be 0. Yep. Absolutely. All right. So, this example is largely straightforward. We've got a hill that's in the shape of a graph of a function. Now, do notice we're looking at a graph now. Won't always be. But in this case, we are. So as we think about this function, keep in mind the picture we're looking at is the graph. One of the weird things about graphs, of course, is that graphs don't live in the domain, and they don't live in the target. They live in this weird kind of combination space that has input variables and output variables on the same axis system. It's pretty weird if you really think about it. So we have input variables x and y, and you can kind of sort of, if you will, think of the domain as being sort of the xy plane in this space. And then the output values, you might call it z. We are, after all, looking at the graph. So the output value, you might think of the target, sort of, kind of, loosely, as being the z-axis like that. So here's the awkwardness. If I want to describe my position on this hill, and do keep in mind the graph is some surface, and in this case it's sort of I'm going to say the surface of a hill, kind of like that. How would I describe where I am on the hill? And let's just step back from the question for a moment and ask, how do we describe where we are? Anywhere on the surface of the Earth. We have a pretty simple answer to that: longitude and latitude. Right? I mean, if you say, hey, I'm at the following coordinates, longitude, latitude, boom, they know right where you are. Nobody needs to go to the trouble to say longitude, latitude, and altitude above sea level, because we kind of figure you're probably on the ground. You're at ground level, whatever that is. Right? So longitude and latitude's enough. Technically, of course, I do have an altitude above sea level. Right now, by the way, we're on Duke campus. We're about 300 feet above sea level, right? Ballpark. So if I describe my longitude and latitude, you're going to assume I'm at ground level. You're not going to assume that I'm 300 feet underground, where z is 0. Right? Kind of makes sense? So we have this, we have a similar issue here that I think is, again, kind of the trickiest part of this problem. So I talk about this point 1, 3, which, again, thinking of the domain as being the xy plane, a little sloppy, but anyway, that's where you might think of the point 1, 3. Is that where I am? Well, no, that's underground. I'm not actually there. I'm at the point sitting above 1, 3, which again, everybody knows that's what you're talking about, right? When you say I'm at 1, 3, of course I'm at the point on the graph sitting above 1, 3. Okay, so just heads up about this conflation, you can complain that this is sloppy, or you can complain that the distinction is uptight. You can go either way with this, right? But fact remains, this is kind of how people talk, and it is kind of on the listener to interpret appropriately, right? So I went to the trouble in this example to say at the point sitting above 1, 3. But in practice, day in and day out, even in this class, by the way, right? Most of the time, the question will just say at 1, 3. Does that make sense to everybody? Okay. All right. Okay, so it's basically all over but the shouting. You want to know which way is uphill? Well, uphill is the direction in which altitude increases the fastest. So I want the direction of fastest increase of my altitude function. That's altitude because we're looking at the graph. So it gives z. And so we take the gradient and we look at the unit vector in the direction of the gradient. It's very plug and chug. It's even a short plug and chug, so that's nice. How steep is it? Well, steepness of the graph is the directional derivative, and the directional derivative, as we just saw, is the magnitude of the gradient. Which, again, easy calculation. Everybody good?
What is the point you plugged in into?
Do what now?
What is the point you plugged in into the?
The point where I am, and keep in mind where I am is 1, 3. So 1, 3 is the A here. Yeah. Is that cool?
Did you say that we're like vertically upwards?
Well, yeah. I mean, so this is the distinction that, the list, it's your job, right? When I say I'm at this point, what I mean is that's the point in the domain. Obviously, I'm not buried underground, right? I'm actually on the surface, right? But how we describe that point and where that point is as far as the input to the function goes is just the X and Y coordinates. Is that cool?
Yeah.
Okay, yeah. So that's actually a really good example of the kind of, what I said was sloppy, but it was conventionally standard sloppy that you had to just be on the lookout for. Yeah. Okay. All right. So here's another cool fact about gradients, a little bit unexpected, but a neat fact. This is about level sets. And again, let's take a moment dramatically to distinguish. Here we were looking at a graph of a function of 2 variables. That surface is a graph of a function of 2 variables. And yes, it's a surface. And yes, here what I've drawn is also a surface. But now this is a totally different kind of picture. This is not something I'm thinking of as a graph. It might coincidentally be, but that's not the point. So the point is that this is a level set of some function f. And of course, since there's 3 variables, x, y, and z, right? This is a surface in a 3-dimensional space. That means that f is now a function of 3 input variables, as I have it drawn here. So, again, you always got to think about the context. This being a level set, totally different kind of a picture of a significantly different kind of a function. Okay. All right. So with that said, I'm going to make a couple of observations, seemingly out of nowhere. Here's my first observation. I claim if you look at a tangent vector, and I mean any tangent vector at a given point A, let's say, any tangent vector. So another way to say that is any vector parallel to the tangent plane. Consider all the vectors that are tangent to the surface at that point. Right? Take any such vector. First observation I'm going to make is that that vector is the velocity vector of a curve that is entirely within this level set. Everybody buy that? Right? This point's in a direction along the surface. So just from that point, just start going in that direction along the surface. And then where you go after, I don't really care. It doesn't matter. So we've got a path there in this surface, and that's a velocity vector. Now, let's talk about what f is doing as I move along this path. And for the moment, let me get rid of the velocity vector even. What's f doing as I move along this path? Keeping in mind this path is entirely in this surface. Keeping in mind that this surface is a level set of f, which means every point on this surface, every point on this curve, f is constant. So, a lot of words. Just to ask the question again for rhetorical purposes, what's happening to f as I move along this surface where f doesn't change? And the answer is that f doesn't change. So, as I'm moving along this curve, f is not changing. As I'm moving along this curve, the rate of change of f with respect to distance is 0 because it's not changing. And that, of course, is also a directional derivative. Give me just a second here. That's a directional derivative And so I can rewrite this as saying the directional derivative in that direction is 0. Yeah.
So, which exactly is the tangent surface?
So we've got a surface here that's some presumably curved surface, right? And I'm just saying this is any tangent vector. So it doesn't matter. Any vector at all that's tangent to that surface. Is that satisfying?
Yeah.
Okay.
I guess, because we drew, one on each side of the
Oh, yeah. Well, so this here is supposed to be the curved surface, as I tried to suggest by these kind of curved. You can see there's a little bit of curve there. I was trying to draw this as being a curved surface. This is supposed to be a flat, what we call tangent plane at that point. Yeah. Yep.
If you assume Z to be F,
but you can't. Very importantly, you can't. You're saying F. So F is the output value of the function.
Yeah.
Very importantly here, X, Y, and Z are all input variables. So you're describing a scenario where, hey, what if this was a graph? And the whole premise is that this is not a graph of F.
But how did you draw that picture if you have 3 input variables?
Well, yeah, if you have 3 input variables,
It's a level
and
set.
it's a level set. So when we say F, it's a
okay.
constant. Yeah. Is that cool?
Yes.
Yeah. All right. Okay. All right. Well, so here's the thing. Rate of change with respect to distance is a directional derivative, and a directional derivative is computed with a dot product because of that formula right there. And so if in that direction, if the rate of change with respect to distance is 0, that tells me this dot product is 0. Where have I heard that phrase before? Again, I hope you all have sort of, knee-jerk reflexes set up. When you hear dot product is 0, you should think perpendicular, technically orthogonal. Right? As long as these two vectors aren't the 0 vector, perpendicular. Yeah.
Wait, so I just want to clarify. We're saying that for a level set,
Yes.
the directional vector of any vector in the tangent plane is
Always 0.
0.
Yep.
Okay.
The directional derivative for any tangent vector to a level set, yes, is always 0.
Wait, could you draw out that picture in say R2?
Oh, well, yeah, so that's right. It'd be a different picture. If F only had 2 variables, then the level set wouldn't be a surface in space. It would just be a curve in the plane. That's right. So a curve in the plane, but the same deal. Any vector tangent to that leveled curve, function's not changing. And just as so here's a very rough sort of picture. If your level sets are like this in 2 dimensions, right? Imagine these being contour lines, and I'm out for a hike, right? Well, if you're moving tangent to a contour line, that means you're at least at that instantaneous moment where you're here. You are literally moving along this curve where altitude's not changing. And so therefore the directional derivative there would be 0. Yeah.
So in that picture, could we think of the gradient as maybe pointing upwards? So
It's somewhat.
To
Yeah.
the vector.
This whole picture is taking place in the domain. Yeah, absolutely. So which direction it points, we're almost there, and I'm about to reveal what that. Yeah. Right. Okay. So what we've found here, by thinking about tangent vectors and observation about how the function changes, blah blah blah, we get down to the gradient's got to be perpendicular to that tangent vector. Well, this applies to all of these tangent vectors. Whatever tangent vector you might come up with, any tangent vector, and the gradient's got to be perpendicular to all of them. Now, how is that possible? How can a gradient vector be perpendicular to all of the tangent vectors? Well, it would just have to be that the gradient is perpendicular to the entire level set. All right, so this, let's see here, color choices. This perpendicularity the gradient is perpendicular to the whole level set. And it's another sort of, I'm going to call this a natural property, right? I mean, perpendicularity is a pretty natural thing to want to talk about. Level sets are a natural thing to want to talk about. And so gradient has a natural relationship to level sets. Okay, yeah?
Is that just at the point A? Or
Yeah, at the point A. Of course, A could be any point. Yeah. Now, so if we were looking at a different point, so instead of this point A, if I were at some other point over here, well, it'd be all different tangent vectors. But it would remain that the gradient at this point would be perpendicular to all of those tangent vectors, kind of like this. And so these two gradients are different, of course, right? But whatever point you might happen to be looking at, the gradient's perpendicular to the surface, yeah.
Even like a little
Up.
yeah, so when you say like a little more.
Okay.
So when you say like as you move along, it's like can you explain like
Yeah.
how are you saying that
So-
it's gonna be zero?
Yeah, because I'm remaining in this set where f doesn't change. Right? If you're moving entirely within this circle, like this surface is defined by f being constant. So if you're moving and if your position is always exactly on the surface, then yeah, the function's not changing. Yeah. Okay, so another neat property. By the way, this gives rise to a cool trick. I'm going to mostly let y'all read this trick. It's a pretty straight read. Fair amount of details. That's a healthy exercise to, think through the details. But I'm going to hit the highlights as usual. We've already talked about finding the equation of the tangent plane. It's the graph of the linear approximation. We argued that back in section, 2.3, if I had to, I don't remember. I think it was 2.3. Anyway, quite a while ago. Here's a different take on how to find the equation of the tangent plane. And this is a good general trick. It goes like this. Suppose you have a surface. And let's suppose that surface is the graph. Keep in mind what graph is, right? Graph of some function f, right? And of course, graph means that you're going to take your function f, whatever that is, right? Whatever that function is, and you're going to set its output values equal to a new variable, in this case, z. Okay, so our s is a graph. Well, okay, sure. Maybe it comes to us as a graph. But just keep in mind, just because something comes to you in a certain way, you don't have to always think of it in that way. You are perfectly welcome and encouraged to, I'm going to think about this differently. Okay? So we've made this observation before. I'm going to do it again, and that is that this algebra is completely equivalent to that. I mean, basically nothing happened when I pulled this little, slight algebraic move here, except that all of a sudden, now I can view this as being a level set. And in particular, it's a level set of now this new function called g. It is not f. This is not f. It's z minus f, not f. So, okay, all right, so this thing came to me as a graph of f. I'm going to say phooey on that. Don't want to think of it as a graph for whatever reason. And I'm going to say, you know what, our surface here, I'm going to reinterpret as being a level set of this other function called g. So with that in mind, because it's a level set, I am allowed to use the calculus of level sets. Very importantly, and specifically, of course, the calculus of level sets as applied to the function whose level set we're looking at, namely g, not f. Can't emphasize that enough. So, what's the win, right? Why would I go to all this trouble to take something that came to me as a graph and reinterpret it now as a level set? And the answer is, well, because the calculus of level sets is totally different tools from the calculus of graphs. And the calculus of graphs is nice, and I can talk about slope of a tangent line and stuff like that, right? But the calculus of level sets that we've just discovered has some pretty cool features to it, and this is one of the big ones. Gradients are always perpendicular to set level sets. Right? So, all right, well, sweet. I have myself a level set here, and so the gradient of that function whose level set I'm looking at, the gradient is perpendicular to the surface. Therefore, it's perpendicular to this tangent plane I'm trying to understand, and therefore I can call it my normal vector. It's a slick move. Very slick move, right? Something came to us as a graph, and we said we're gonna do a little sidestep here. We're gonna reinterpret this as a level set of a different function, and reapply the calculus of level sets, which gives me exactly what I needed. Again, our goal here being to understand the equation of the tangent plane. And the most important thing in understanding the equation of a plane is finding its normal vector. So details to follow. Make sure to read those details. That's the big idea. And this is a really powerful idea in multiple contexts. This example that, oh, by the way, notice we do get the exact same equation for the tangent plane just like we had before. So that's good. But notice, as in an example like this, you don't even need to have initially thought of it as a graph. I mean, I set this one up to be a, let's see here, I set this up as being graph of some function f, but how about I just say fooey on this, and I just want to find, you know what, I shouldn't have crossed out quite all of that. Oh gosh. Let me do that again. What if I wanted to find the tangent plane to that level set? It might even be phrased more simply as find the equation of the tangent plane to that surface. It might just come to you as just an equation. It doesn't have to be initially thought of as a graph. Any equation. You want to find the equation of the tangent plane, play the same game, take the gradient, that's your normal vector. Other details you got to think through, y'all can think through those details. But very general idea. Okay. Alrighty. Okay, new topic. The implicit function theorem and implicit differentiation. Now, this is the topic that I find that I have the most difficulty with clock control. Right? If I were to talk about this topic the way I'd really like to, I would spend probably at least a full class on it, maybe a class and a half. And we don't have that kind of time. We just can't. So I'm going to do my best to restrain myself from going on at length about things that I think are really fascinating, but that don't really quite meet the bar for how to spend our very valuable class time. So anyway, here's the big question. Suppose you have a curve, in particular a level set in the plane. Right? We're going to stick to two variables for this quick moment. Can I view this level set as being a graph? Can I view y as being a function of x? Right? And now I do have to talk about an important detail. The question I'm going to ask is locally. Right? To the global question, if I were to say, in full generality, is this a graph? Well, obviously not. It fails the vertical line test. Instant loser. Right? But that's not the question I'm asking. I'm asking the subtler question as follows. Oh gosh, can I get the subtler question is, given a point that I might be looking at, if I were to look locally, that means just take a vicinity, what we call a neighborhood, of the point in question on the graph. If I were to look just at only that part of the graph, if I were to look just at this part of the graph, like so, on just that part of the graph, can I view y as being a function of x? In other words, does that pass the vertical line test? And why, yes, it does. So locally, near that point, yes, this is a graph, or said differently, I can locally view y as a function of x. And by the way, and here's where it gets a little surprising, that works at this point as well. And now you're thinking, oh, but look at those, wait, but up above, it's going to hit 3 times. Again, not locally though, right? Again, locally means I look in a little vicinity like that. By the way, you get to pick how small you want your neighborhood to be. It'll be as small as you need it to be, right? And locally, again, passes the vertical line test, no problem. Everybody on board? So really the only place we ever encounter a problem, if I want to view y as a function of x, the only place I would encounter a problem would be a point like this one. Because at that point, notice any neighborhood, no matter how small, any neighborhood of that point, the resulting curve is going to fail the vertical line test. Everybody see that? All right. Now, who cares? Right? Always an important question to keep in mind, right? What are we doing? Where are we going with this? Why should I care? And the reason we should care is because when you see algebra like this, and in this algebra, you see x and y are both input variables, or said differently, x and y are just variables in an equation, and it's not at all a given that I can solve for y. In fact, I might literally not be able to solve for y. In this case, as the curve I've drawn, you cannot solve for y. But you might still want to be able to talk about dy dx. And what's that got to do with anything that we've been doing here? The answer is that this is a derivative. And you've got to remember what derivatives are applied to. Derivative is something you do to a function. It's not something you do to a variable. Sometimes the variable represents the value of the function. But the point is, the derivative is something you do to a function. Period. Right? Look it up in any calculus textbook. The definition of a derivative, they talk about the derivative of a function. So when you write down dy dx, you are implicitly suggesting that y, at least for the purposes of being able to talk about rates of change, in other words, at least locally, you're suggesting that y is at least locally a function of x. And if it is, that's fine. But if it isn't, this is garbage nonsense. Meaningless nonsense. And this is not a good thing. Right? This is something mathematicians are always scared of. I want to make extra sure that when I write stuff down, it isn't meaningless garbage. Is everybody happy with that? Right? Does that make sense? Okay. So a classic version of this that y'all have probably seen is, if I can get this thing to cooperate, here we go. Y'all have probably seen this move in a Calc 1 class where they take a unit circle and they say, let's find the slope here. Let's find dy dx. And so they start taking derivatives, and they'll write down 2x plus 2y dy dx equals 0, and then you solve for dy dx. Does that look familiar to everybody? Y'all have seen something like that before? Perhaps. Well, here's the problem. This is fine at a point like that, or at a point like that, or at a point like that, but not only is this wrong, but also that is meaningless at a point like that. At this point, not only can you not solve for dy dx, not only can you not talk about dy dx, you can't even talk about y as being a function of x, much less take a derivative of it, much less be able to find it. Is that cool? High schools are notoriously bad at kind of sweeping points like this under the rug. And that's, anyway, this is not a high school class. We're not going to sweep this under the rug. So this is something we have to worry about a little bit. Okay. All right. So how do we address this problem in practice? So in practice, we make an argument. And again, I'm going to let y'all think through the details here. But the big idea is that problems look like, let's see, I'll do this in red. Problems look like this. It's where the curve is kind of wrapping under itself in some sense. So that's what our problem looks like. And then I make the modest observation that if the curve is wrapping under itself, then that means it has a vertical tangent line. And if it has a vertical tangent line, that means it has a horizontal gradient, because after all, gradients are always perpendicular to level sets, which is presumably what we started with. And that means, what would it mean for the gradient to be horizontal? Well, it would mean that its second coordinate is 0, and that second coordinate is that y partial. So that's basically the argument, and so any point that has a problem would be characterized by the y partial of f being 0. And then that statement, we're going to turn that around backwards, upside down and backwards, you might think of it. So this is the contrapositive. So the contrapositive is that, well, then if the y partial is not, wrong color, if the y partial is not 0, then there can't have been any sort of problem that would require that partial to be 0. And so this is our sort of first version of the implicit function theorem. First version of the implicit function theorem is that if the y partial is non-zero, then yes, all good, no problem. Yes, you can view y as, at least locally, view y as being a function of x at that point. And this generalizes very nicely. Here's the three-dimensional version. And again, it kind of has the same sort of take. Problems are going to happen at points where you're in the process of wrapping under, where the level set is in the process of sort of wrapping under itself. That's where you're not going to be able to, define z as being a function of x and y. And if that is wrapping under itself, you have to have a vertical tangent plane. And if you have a vertical tangent plane, then you must have a horizontal gradient, and that means the z partial would be 0. Yeah?
So if you see, based on the point, you have, different derivatives?
Say it again, please. I'm sorry.
So, based on where the point is on the curve,
Yeah.
you're going to have different.
Oh, well, yeah, sure. Right, because you talk. Let's go back to this picture here. At this point, yes, I can solve locally for y as a function of x, and the derivative would be, well, as I have it drawn here, it looks like about 0, maybe a little less than 0. At this point, y is locally a function of x. Also, yeah, sure. Here the slope appears to be a little greater than 0. And, pick your point. At a point like that, again, no problem. There the slope is larger. Absolutely. Did that answer your question?
Yeah.
Okay. Yeah. Cool. Okay. All right, so there's a pattern in these two examples that we've kind of, I know we've gone through this very quickly, but again, this is, it's cool background, and I want y'all to have at least an inkling of where these formulas come from that we're going to be using. But notice, whatever variable you are hoping to view locally as a function, it's partial with respect to that variable that you need to look at. In the first example, I was asking if I could view y as a function, and it ended up being the y partial that I have to look at. If I want to view z as a function, it ends up being the z partial. And I'm just going to assert this is not a coincidence. This is the pattern. And so that's how we're going to state this general theorem here, general version of the theorem. And that is, if you're looking at a level set of an appropriately nice function, this is regularity, you got to worry about that kind of stuff. Just don't worry about that part. And if you're looking at a level set, very important, f's got to be constant. That's how our argument sort of went down. If you're looking at a level set, if you want to view one of those input variables locally as being a function of the others, look at the partial with respect to that variable. And specifically, you're taking a partial of the function whose level set you're looking at. Is that cool? So whatever function you're looking at a level set of, if your equation comes to you, by the way, not written as a level set, rewrite it so that its stuff equals constant. You've got to write it as a level set. So whatever you're looking at a level set of, take its partial with respect to whichever variable you would like to call a function. And non-zero means yes, you can. So this is called the implicit function theorem. Okay, so let's apply this in action. Here you go. And by the way, I think this is a pretty cool example in the sense that we're looking at this surface here that I have no idea what this looks like. Right? I'm not going to use my geometric intuition here for, that's a sphere or something like that. Make some sort of a drawing of it and then appeal to your sense of geometry. Not at all. Right? I haven't got the slightest clue what this actual surface looks like. But for whatever reason, I'm interested in looking in the vicinity of that point 1, 2, 3, and I would like now to view x locally as a function of the other two variables. Now again, if you were thinking about this geometrically, you'd have to, then I want, if this is going to be a function of that, then my vertical line test is now kind of a horizontal line test, and the geometry can get confusing, right? Legitimately confusing. So here, no such concerns. If you want to answer this question, can I locally view this as a function? We're going to look at whatever function I'm taking a level set of. I'm going to take its partial with respect to whichever variable I would like to view as being a function of the other two. And then you plug in the point in whose vicinity you want to actually address this question. And as we got in the theorem, we got an answer which is not 0. And so the answer is yes, indeed. Locally, at least, near this point, the surface described as a level set of this function, I can locally view x as being a function of y and z. And so, for example, then what I get out of this is knowing that x is indeed a function of y and z, I can talk about the partial derivative of x with respect to y, or I can talk about the partial derivative of x with respect to z, because it's a function of y and z. Yep.
Could you like scroll up to the that line?
To up here?
No, other up.
Further up?
Yeah.
Okay.
This one.
Yeah.
So the tangent lines that you were drawing,
Yeah.
are they partial of f, partial y?
No, because I'm not looking at a graph of f. Right. So this is a level set of f. So there is no partial f on this picture. F is neither of these axes. Does that make sense?
So when you draw a tangent line, that's just partial y with dy
Well,
by dx.
If I were to talk about, let's say, at a point like this, and at that point I talk about its tangent line, and if I wanted to talk about the slope of that line, well, slope we tend to think of as being rise over the run, so that's going to be the sort of the change in y per unit change in x. And so, yeah, what we call the slope of this line would be dy dx. Or said differently, dy dx, a derivative that we might reasonably want to compute or be able to compute, dy dx would tell me about this orange line. It would tell me, what's blue divided by green? Right. Yes.
We go back to the equation.
Back to where? The example?
Yeah.
Okay.
So now that you said that like it's a locally functional.
Yep.
So can you write the equation in terms of that?
Well, in some theoretical sense, maybe, kind of. Now, that doesn't mean that I will have the algebraic chops or even that algebraically it would be possible to literally write x equals and have a formula that I can write down. In this case, for example, I don't know how to solve cubics. Right? And I guess it can be done, and if I put my mind to it, I'm sure I could. But make it a x to the 7th, and no, you can't do that, right? You can't actually do the algebra. But that's not what the implicit function theorem is asking. The implicit function is asking not about how does the mechanics of algebra work, but is it theoretically possible in the sense of is it true that for every y and z there will be exactly one value of x? And whether I can do that algebra is not really quite what we're doing yet.
So based on this, you can take partials
Yep.
of x with respect to y.
That's right. Or x with respect to z, either or both. Yeah, absolutely. Okay, all right. Now that brings up a natural other question, which is, okay, if x is local, went in the wrong mode here. If x is locally a function, therefore I can talk about its various partial derivatives, how would I compute those various partial derivatives? And is there a handy-dandy formula that will save me having to kind of go through some process, some algorithm every time? And the answers are yes and yes. There's a lovely formula for how to do this. Here's the big idea. And again, I'm going to do this in general. I'm going to show you two different ways to do it. Well, I'm going to wave my hand at one way to do it. And if you really want to get real strict and proper about it, I kind of have to set up, this is a little bit annoying. You've got to define some new variables, x1 prime, x2 prime, etc., like this. Why do you have to do this? Well, because y'all may recall way back when we were doing the chain rule, I made this gripe, which is when you got a bunch of algebra written down, if that algebra gives rise to a diagram that is not a composition of functions, then we don't have a chain rule to do business with. There is no chain rule that we've seen anyway that will directly address something like this. Okay? And so we have to play fancy games and introduce new fake variables, like this, x1 star, so that all of a sudden now this is a composition, and then I can use the chain rule. So that's what was going on here is I had to introduce a bunch of new variables to avoid this this kind of like, illegal diagram sort of problem. Well, here's the good news. Yes, this diagram that I want to work with instead is not okay. This violates my own rules. As I have it written, this does not appear to be a composition of two actual functions. But this is going to be, I'm going to say, intuitively satisfying. And if y'all are willing to trust me that the crimes we're about to commit will not lead to any problems, it's victimless crimes, it's actually okay, it's no problem, this is a much easier way to think about the situation that we have at hand. So here's the situation. We have, f initially is a function of all these variables, and we're looking at a level set defined by where that f is equal to a constant. And then I've argued that because of certain partials not being 0, I can view one of these variables, in particular xi, as being a function of the others. So I'm just going to do it like this and say, well, let's just not forget, not only does f depend on all these variables, but xi itself can be thought of as a function of everything, all of the x's other than itself. And yeah, I know I'm being a bad example, and I apologize. But again, take your choice if you want to go through and think of it this way. It's a lot uglier and less intuitively satisfying. So here's the big idea. If we have it set up like this, with the understanding that xi is a function of all the other variables, and if I want to take a partial derivative with respect to xj, now let's think it through. What does that mean? Partial of xi with respect to xj means, okay, well, I got to hold all the other variables constant. Okay. I'm going to hold all the other x variables constant. So all of these are going to be constant. All of those are going to be constant. All of these are going to be constant. And only xi and xj are allowed to change. And now, let's try to capitalize on the fact that we know that f is a constant. We are, after all, looking at a level set of f. And if f is a constant, then the overall rate of change of f is 0. F is not allowed to change at all. So grand total, the derivative of f has to be 0. And then you just think through the two different paths, and there's this path, which gives you that term, and then there's this path, sort of a two-step path that gives you this term, and again it adds up to 0. And again, what we're looking for, okay, I need a color. I'm kind of out of colors, aren't I? I'm going to use yellow. It's hard, yellow doesn't show up very well, but this partial derivative that I'm looking for is right there, and I could just solve for it. And there is my handy dandy formula. So I encourage y'all to memorize this formula. It's very useful, very convenient. Plug and chug. Streamlines the whole process. Does a lot of the thinking for you. That's cool. Everybody buy it? Now let me warn you about something. There's a notational warning. This is a very common mistake. I've seen this following mistake made many times, and that is a lot of students just cannot help themselves, but they gravitate so much toward the following, and that is to say, well, this and this. I'm going to go ahead and put a great big X, okay, because what I'm about to do is super wrong. And it gives me the creeps to even do it, right? But I see the following a lot, and that students say those are the same, so we'll cross those out. And then the denominator of the numerator is the denominator, and the denominator of the denominator is the numerator. And then they figure must not be any need for that minus sign right there. And so a great many students will just fail to put that minus sign in there. And that's a huge problem because that's wrong, right? First of all, it's nonsense reasoning, treating these things as fractions just because we write them as fractions. Which, again, unfortunate, right? But again, very importantly, they are not fractions. This partial f and this partial, neither one of those is really a well-defined thing by itself. So canceling them is just nonsense, right? So now we get to a logistical matter, which is, okay, well, yeah, but what's the big deal? It's just a minus sign. We all make sign errors. I know I do. Right? I make plenty of sign errors all the time. I do my best, but oh my gosh. How come this isn't just a sign error? And the reason is that there's different kinds of sign errors. There are sign errors that, again, the innocent, we all will have, 5 minus signs and somehow they all cancel. We've all done it. I know I have. And that's just, I counted wrong, right? Or something. That's just silly nonsense, right? That's not what this is, right? Leaving out this minus sign makes it look like you're thinking about these things as if they're canceling. And you got to keep in mind, we have to grade on the basis of what's written on the page. And if you write it down as is, I've got it right here, namely without the minus sign, what you've written looks like you think he's canceled. And it's such a bad look, right? And again, I have to grade on the basis of what I can see on the page. So it's a little bit frustrating, and again, you can think of this glass half full, you can think of this as glass half empty. The glass half empty take is, I get a big penalty if I forget that minus sign. The glass half full take is, you get points just for remembering a minus sign. So let's take the positive, optimistic view on this situation. That is easy money. Just make sure to remember this minus sign, right? Make sure to remember that minus sign. And that's very much to your advantage. Everybody good? Okay, by the way, in some sense, where does that minus sign, give me 2 seconds, where does that minus sign come in, morally speaking? Why, it seems like what are the odds? Why is it exactly a minus sign, when it feels like it should be, no minus? It's too close. How is this? Seems like a coincidence. And the answer is literally that how much f changes moving along that path, which is arguably, if you want to say, it's kind of what that partial f would be how much did f change moving along that path? And then, on the other hand, how much did f change by moving along that path? Well, that's kind of, if you will, what that one would be. The whole point to this argument is that f is not allowed to change, and that therefore these two terms must cancel, and that therefore these two things really should be negatives of each other. That's how things cancel. It's not that these two things should be the same because they're written the same. It's that they should be negatives of each other because they literally have to cancel each other. This is just kind of touchy-feely, right? Does that make sense to everybody? Is that satisfying, I hope? So, hopefully that helps. Yes, you had a question.
So in the problem,
Yeah.
You have to always figure out whether it's locally variable.
Yeah. No, I'm going to totally address that. That's coming up. Yeah. Great question. Totally going to get to it. Let's. I want to get one under our belt first, though, with this equation, and so we're going to go back to the same example we were just looking at. Same surface, same equation, same point. We've already established that x is locally a function of y and z. We're just picking up where we left off with that previous example. And let's compute the partial of x with respect to z. Again, if x is locally a function, then I can talk about its partial with respect to one of the variables it's a function of. Okay, so I'm going to say pretty much this is the equation from the previous page. Now, how did it's not literally exactly character for character of the equation from the previous page, but this is the manifestation of that general equation in this case. Let me show you how I remember this. And it's a little bit embarrassing. I cringe a little bit every time that I think about this, but this works. Take it to the bank, reliable. The first thing I do is I think to myself, well, I'm not going to forget this minus sign. I'm going to get those points, and the very first thing I do is I write down the minus sign, or at least that's the practice I try to hold myself to. Get that minus sign on the page, right? Make sure that you don't forget it. That said, and here's the cringy part, I literally think to myself, wait, how is it that garbage argument goes about nonsense cancellations that seems to give everything but the minus sign that I've already remembered? And I get a little embarrassing, a little cringy. I go through the garbage argument because it will always get the variables in the right position. And so, partials of f go there and there, that being, of course, the thing whose level set we're looking at. And the thing that is going to be, well, let's see here. This is my sort of denominator differential, so that must be the denominator of the numerator. And this is the numerator, if you will, of what we're looking for. So that must be the denominator of the denominator. And boom, there's my formula. And as long as you don't forget that minus sign, this will work just fine. Is that cool? This spares you having to think through this argument every single time and write down and think about the different two different paths and doing this and doing a little bit of algebra. It's just nice to have this little shortcut. So anyway, that's how you get that formula, and then it's all over with the shouting. You compute the appropriate partials. You plug in the appropriate point. Right? And then, boom, arithmetic and victory. Everybody see how that works? Okay, last thing, your question. So, short answer, yes, you got to do both parts. You have to first establish that the thing you're looking for a partial of actually is a function. Right? If ultimately the question is, hey, what's the derivative of that bicycle? Then you should say this is a garbage question. It doesn't make any sense. Right? Don't try to take the derivative of a bicycle. It's meaningless nonsense. So yeah, you first have to establish that the thing you want to take a derivative of is actually a function, and then you actually take the derivative with the formula we just looked at. So in particular then, if the question says, and I'm just going to do like so. If the question says, here's a surface, and near that point, what's the value of that partial derivative? Right? The very first thing you should think of is, wait a second. He's asking me to take the partial derivative of a thing that I'm not even clear is a function? What's going on here? What kind of nonsense is he asking me here? Right? I haven't established that x is a function of anything. You cannot go around taking derivatives of bicycles. It doesn't mean anything. It's all nonsense. So if I'm supposed to take a derivative of x, I better figure out and establish that x is actually a function first. And so the very first thing you would do is you would write, is x locally a function of y and z? This thing you want me to take a derivative of? And then you would apply the implicit function theorem by taking that partial, observing that it's not 0, and therefore, yes, x is a function. And then, having written all of that down, you would then do this calculation like that. Two-step process. And by the way, I've got a long precedent of these kinds of questions on my old exams. And again, your reminder, this course is Math219, but Math212 that I taught for a very long time before this is a practically identical course. Those old exams are also very representative, or they're not perfect, right? There are little differences, of course, but certainly a good supply of practice questions for y'all in those old Math 212 exams. So on all of these exams, you can look back and find various examples of implicit differentiation problems, and FYI, about half of the points go to establishing that the thing you've been asked to take a derivative of is actually a function. It's about half of the points for the question, right? And then the remaining half of the points go to the actual computation and getting a number. Okay, so there you go. Okay, right. So moving along. 3.2 is actually really quick. I'm gonna take it as my goal to finish 3.2 today, and the way we're going to do that is we're basically not going to do most of it. 3.2 is, it's a kind of a cool topic, a little bit of a digression, and reparametrizing by arc length it's just a little algebraic process, and we're not really going to do anything with it, so I'm not going to worry about it for the moment. But this stuff up here at the beginning is important, and we do need to do this. We'll call it a day when we're done with that. It starts off with the idea that we have a parametric curve, something, let's say, maybe about like that. And I want to talk about this thing called the dr vector. dr. And keeping in mind r represents position, and keeping in mind that differentials are linear approximations of changes. So dr represents a linear approximation of how much does my position change. And if you're at this point, dt seconds later, you'll be at some other point, sure, and it curves a little bit, but based on how things are going at this point, if you make a linear estimate, it's going this way for the moment, and so your linear estimate of your displacement would be a vector like this, and it would be off a little bit, because linear estimates are always a little off. Okay. So that's what we call the position differential, because r is literally position, and this is its differential. All right. No surprise, I hope, that dr is r prime dt. All that says, if you want to think about it from a geometry point of view, is displacement is velocity times time. Which, of course, you can rewrite because r prime is velocity. And then let's talk about ds. Well, s in this context represents distance. And so ds means what is our linear estimate of how much distance I've traveled. Not the vector displacement, but just, in terms of my odometer on my car, how much distance did I move? And I make the case, I think this is plausible, that your linear estimate of distance is just the magnitude of your linear estimate of displacement. So I hope that's a reasonable formula there. Is that cool, everybody, so far? Okay. Where things do get a little sort of confusing is what justifies this, wrong color, this formula for the dr vector. And there's a couple of different ways to think about this that I think are reasonable. One way to think about this is, really the most natural way to think about this is this dr vector, well, it's a vector, It has a direction and a magnitude. What direction does it point? The direction that it points is a unit vector pointing in the direction that it's going. And we know how to do that process, how to find a unit vector. Unit vector that represents a direction. And what's the magnitude? Well, the magnitude is ds. So when I claim that dr is TDS, all I'm really claiming is that, well, this is the direction it's pointing and this is the magnitude it has. And direction and magnitude is what a vector is. So that's, I think, really the best way to think about it, arguably the most natural way to think about it. I don't know, I should have circled that just for consistency. So that's one way to think about it. The other thing you can do, if you want, instead, you can also say, now let me try to remember how to do this. View T by that formula and view ds by that formula, and now green times blue, this times that, makes this product equal to this, which we've already agreed is this. So if you want to just rely on the algebra, then there's some algebra that makes it work. But I kind of prefer the direction and magnitude point of view. Okay, so heads up, FYI, this dr vector, right, and all of these various related players and relationships, all of this stuff is going to figure very prominently when we get to chapter 6 and 7. It's going to be a really big deal, one of our primary tools. That's why I'm making a big deal out of this here. And we're not going to do terribly much with it for the moment, but it will be a big deal later on. And we're gonna skip the rest of 3.2. Okay, so I'm going to draw the line then right here, and we will pick up tomorrow with vector fields. Okay, see y'all later. Have a good one. Office hours in 12 minutes, of course.